Welcome back. Recall we had this big picture at the end of the last video. We have markers stuck to our subject. We're going to collect the locations of these markers. We'll define tracking reference frames. We'll use some information we collected in our calibration process to determine where the anatomical reference frames are, and ultimately relate anatomical reference frames on adjacent body segments to define joint angles. What we're going to see in this video is how do we do all these calculations. All these gray arrows are transformation matrices, or they relate one reference frame to another reference frame. We'll see how we do these calculations. We've been talking about them already. Let's just make sure we know precisely how they're defined. We need two pieces of information, in fact, to define a reference frame. We need to know the origin, which is simply a point, and we need a basis. We can define a basis using three mutually orthogonal unit vectors. So 3 unit vectors. Okay, so let's define a frame over here. We'll call this frame A. The origin is AO, and here are the basis vectors AX, AY, AZ. We'll make sure it's a right-handed frame by computing AX cross AY and make sure our thumb is pointed in the direction of AZ to remember the right-hand rule. Let's define another frame over here, frame B. The origin is BO, and the unit vectors that define the basis BX, BY, BZ. Now, how are these two frames related? Clearly, they're in different locations and they're pointed in different directions. And these are, in fact, the two ways that we will relate to reference frames. In fact, we'll relate them using what we call a transformation matrix. And there are two pieces of information that are encoded in a transformation matrix. One is the translation, or the relative position of the origins of the two frames, and the other is the rotation, or their relative orientations. And we'll use rotation matrices to define these rotations. So let's take a closer look just at that translation part. We'll spend a little bit of time looking at the rotation part after this. So first, we have frame A here, origin AO, unit vectors AX, AY, AZ, as we had before. And I'm going to draw this potato here in space. Multi-body dynamicists like drawing potatoes. So here's a potato, and here is a body fixed reference frame, BX, BY, BZ, with origin BO. Now, what is the translation between frame A and frame B? More precisely, we want to know, for instance, what is the location of BO expressed with respect to frame A? As a vector, that looks like this vector here, okay, a vector from AO to BO. Let's call that P superscript AOBO. And now where is BO with respect to frame A? Well, what we're going to do is move along the coordinate directions of frame A in order to arrive at BO. So let's imagine we're walking along AX. We have to walk that far. Then we'll walk along in the AY direction. We'll walk that far. And then we'll walk in the AZ direction. And we'll walk that far. Okay, so we walked a distance of, let's say, PX in the AX direction. Then we walked PY in the AY direction. And then we walked a distance of PZ in the AZ direction in order to arrive at BO. We might express that in a couple of different ways. So let's write this first in unit vector notation. So we might write P superscript AOBO equals PXAX plus PY AY plus PZ AZ. So we're moving PX in the AX direction, PY in the AY direction, PZ in the AZ direction. Another way we can write this is in matrix notation. In matrix notation, we're actually going to add an A subscript here. The reason we need the A subscript, the subscript itself is not super important. What it represents is very important. What it represents is the frame with respect to which these three numbers are expressed. So this vector will contain just three numbers, px, py, pz. Unlike in unit vector notation, where we know ax, ay, and az, they're written right there in the equation. So when we write p in matrix notation, we need these little subscripts to keep track of the frame in which these coordinates are expressed. Let's now look at the rotation part of the relationship between two reference frames. And what we're going to do is just look at an example here, just to keep it simple. So let's suppose that we have two frames, once again. Here's frame A, AX, AY, AZ, frame A. And here's frame B over here, frame B, BX, BY, BZ. So by inspection, we can see that frame A and frame B are related simply by a rotation of 90 degrees about the x-axis. And in fact, the rotation matrix RAB, this is the rotation matrix that relates frame A and B, will be defined as follows. The first row is 1, 0, 0. The second row, 0, 0, negative 1. And the third row, 0, 1, 0. Now let's take a minute and understand what's encoded within this rotation matrix. First of all, notice that I put a superscript on the left and a subscript on the right. These will help us keep track of what frame we're referring to. You'll see in just a second when we write out the equation that relates vectors expressed in these two frames. The rotation matrix contains a lot of very useful information, and it depends kind of how you look at the rotation matrix. Let's just start off by looking at the rows. The first row of the rotation matrix contains the coordinates of AX relative to frame B. So the coordinates of AX relative to frame B, we can write this in unit vector notation. Using the first row, we would write AX equals 1 BX plus 0 BY plus 0 BZ. Is that true? Well, let's look at AX. Here's a vector over here. Imagine expressing it relative to coordinates in frame B. What would we need to do to generate that vector using combinations, linear combinations of the basis vectors from frame B? Well, we just need 1 BX because AX and BX are parallel. Let's try the second row. The second row says that AY equals 0 BX plus 0 BY minus 1 BZ. Is that true? Well, if we took AY and expressed it in frame B, you can imagine drawing AY over here. There's AY living in frame B's world. How do we express AY using the basis vectors from frame B? Well, it's simply pointed in the opposite direction as BZ. Hence, AY equals negative BZ. And finally, for the third row, AZ equals 0 BX plus 1 BY plus 0 BZ. Is that true? Yes, indeed. AZ is pointed in the same direction as BY. So that's what's encoded in the rows of the rotation matrix. What about the columns of the rotation matrix? In fact, the columns tell us the same thing, but the other way around. For example, the first column says BX equals 1AX plus 0 AY plus 0 AZ. Well, we knew that already. BX and AX are parallel. How about the second column? The second column says BY equals 0 AX plus 0 AY plus 1 AZ. Is that true? Well, imagine taking BY, putting it in frame A, and expressing it using the basis vectors of frame A. We would need 1 AZ. And similarly for the third column. So that's how we can read what's in a rotation matrix. What we actually want to do is generate these rotation matrices, kind of go the other way around. We'll see that in just a minute. Okay, let's try one more thing. Let's imagine we have a vector V. We'll draw this vector in both frames. Here's V in frame A, here's V in frame B. What if I had the coordinates of V with respect to frame B, and I wanted to compute them in frame A? How would I do that? Here's a nifty equation that will do that. VA equals R from A to B times VB. The way we've defined our rotation matrix means that if we have the coordinates of vector v with respect to frame B, we can multiply it by the rotation matrix to get the coordinates of this vector with respect to frame A. So let's try it out. Let's try multiplying our rotation matrix, R from A to B. This is 1, 0, 0, 0, 0, negative 1, 0, 1, 0. And what are the coordinates of vector v with respect to frame B? Well, it looks like it's 0 in the bx direction. It looks like it's 1 in the by direction and 1 in the bz direction. Okay, so let's perform that multiplication and see what we get. The first element in this vector will be a 0. The second element is a negative 1. The third element is positive 1. So what we're saying is, at least we think, the coordinates of vector v with respect to frame A are 0, negative 1, 1. Is that true? Well, let's look at our picture up here. Is vector v 0 in the ax direction, negative 1 in the ay direction, and positive 1 in the az direction? Yes, it is. So this equation seems to be right. Also note that we could invert this equation. We could write vb equals r from b to a times va. But notice that the definition of the rows and the columns are sort of opposite of each other. So you can imagine, hopefully, going from frame A to frame B and going from frame B to frame A are very similar. They'll use a lot of the same information, all the same information in fact, but the rotation matrix will just be the transpose. The rows will become the columns will become the rows. So we can also write this equation at the bottom as the rotation matrix from A to B transposed times VA. And we'll also note just briefly that the transpose of a rotation matrix equals its inverse. So we looked at the translation part, we looked at the rotation part. Let's put it together and define transformation matrices. These are 4x4 matrices that describe the relative position and orientation of two reference frames. So I'll just write down T from A to B, very much like the rotation matrix. We have a 4x4 matrix here. The last row is always 0, 0, 0, 1. It will always be the case in the work that we do here. You might use these in other contexts, but not here. In the top left corner, we have our rotation matrix, R from A to B, that describes the relative orientation of frame A and frame B. And over here in the top right corner, we have P AOBO, or the vector from the origin of A to the origin of B, expressed in frame A. And there's our transformation matrix. So in one matrix, we encode the rotation as well as the translation, and we can compose translation matrices the way we would compose rotation matrices. If we're rotating from frame 1 to frame 2 to frame 3, we can multiply these rotation matrices together to go straight from frame 1 to frame 3. We can do the same thing with transformation matrices. And if you recall that big diagram we had with all the frames floating around, this is what we're going to do with these transformation matrices. We'll perform matrix operations to ultimately compute, for example, the knee joint angle. Another thing to mention about rotation matrices is that the order matters. You have to be careful about which order you perform the multiplications in. Same with transformation matrices. This is just an example that shows this. So we have a book here with a body fixed frame, bx, by, bz. So imagine that frame being welded or glued to the book. And we're going to perform body fixed rotations, which means we're always going to rotate about an axis that's welded to the book. So we're always going to be rotating about these green axes that are glued to the book. And we're going to go in the order x, y, and then z. If you're south of the border, that would be x, y, and then z. So we'll start off in this orientation. And first, we're going to rotate about x. And each time, we're going to rotate by 90 degrees. Okay? So let's imagine we're going to rotate it by 90 degrees about this axis here. So imagine you can point your thumb in that direction, curl your fingers around, and rotate the book in 90 degrees. So you just see it flop over. And that's what we see in that first picture over there on the left. So we have rotated this by 90 degrees about the bx axis. Now let's do the same thing, but for the by axis. So where is by? By used to point this direction. Now it points up. So we're going to rotate by 90 degrees about the vertical axis now, by. And you should see the book kind of rotate towards you. And that's what we have in this image here. And finally, we're going to do 90-degree rotation about bz. Once again, it's bz. And here's bz now. Do a 90-degree rotation. The book will fold over onto its back. And there we have the book in its final orientation. Now we're going to do the same thing, but in a different order. We're going to do z first, then y, then x. Still body fixed rotations, but we're going to do them in the opposite order, just to demonstrate that we'll get the book in a different orientation. So we'll start from the same orientation up here. First, we're going to rotate about z. So imagine pointing your thumb upward, curl your fingers in this direction, and the book will end up pointing in that direction there. Next, we'll rotate about by. By now points into the screen, so we rotate by 90 degrees. The book will come towards us. And finally, we're going to rotate about bx. Bx now points down, so we'll rotate this way. The book will spin around and face us beneath the plane, but it's pointed towards us. And if you compare the final orientation with a body fixed XYZ rotation sequence versus a body fixed ZYX rotation sequence, you find that the books are in different orientations. So it's very important to get your rotation sequences correct. Now let's take a look specifically at what the rotation matrix would look like if we had a body fixed ZYX sequence. So what we're going to do, we have the rotation sequence shown here. We're going to write down what the rotation matrix would be. And remember that I said we can combine rotation matrices by multiplying them together. That's exactly what we're going to do here. So imagine we want to perform body fixed rotations, first about z, then about y, then about x. How do we do that? We can do that by multiplying together elementary rotation matrices. Elementary rotation matrices are simply rotation matrices where the rotation is about one of the coordinate axes. So the first rotation, we're doing about the body fixed z-axis. So we'll have a matrix here that is r sub z. You might see that terminology in some places. The elementary rotation matrix, when the rotation is about z, looks something like this. We have cos theta z, negative sine theta z, sine theta z, and cos theta z. Make sure you get the negative sign in the right spot. So that will be the first part of our rotation matrix. Now we'll multiply with the rotation matrix that represents rotation about y. I know that the middle column and the middle row will be 0, 1, 0 because we're rotating about y. The y-axis is not going to move if we're rotating about y. Okay, the other entries will be cosine theta y, sine theta y, negative sine theta y, and cosine theta y. And finally, we're rotating about the body fixed x-axis. The elementary rotation matrix looks like this. We have cosine theta x, negative sine theta x, sine theta x, cosine theta x. Now we'll multiply them together, and we'll end up with something on the next slide. So let's try this. Let's assume we want to compute phi, theta, and psi, and we'll assume that r11 through r33 are some numerical values. So we'll just relate elements of this numerical matrix to elements of this symbolic matrix, and then we can use some trig to solve for the angles. So for example, let's look at this entry here, r32. If we assume body fixed ZYX rotations, then r32 will be equal to this element of our symbolic matrix. So r32 equals sine phi cos theta. Similarly, r33 will equal cosine phi times cosine theta. Now what if we divide them? r32 over r33 equals sine phi over cosine phi. Looks a lot like tan. Therefore, the angle phi is a tan 2. Now we'll use the 2-argument arctan so that we resolve into the correct quadrant. It will be a tan 2 of r32, comma r33, because this is tan of theta. We can do a similar exercise for the other 2 angles that we don't know. So for example, psi, we have arctan 2 of, and we'll use r21. Here's sine psi, r11. This component contains cosine psi. When you divide them, again, the cosine theta cancels, and we'll end up with just r21, comma r11 here. You can do a similar thing for theta. I'll write it up here. Theta equals a tan 2. And now we need some expression with sine of theta and some expression with cosine of theta. So we can compute, we'll end up with the tangent of theta, and we can use the a tan 2 function similar to the other 2 angles. R31, for example, this is negative sine theta. So sine theta equals the negative of R31. So this is negative R31. Finally, how do we get cosine of theta? We can use R11 and R21. You notice from R11, if we square it, we'll get cos squared theta, cos squared psi. For R21, if we square this, we'll get cos squared theta, sine squared psi. If we now add the 2, we'll get cos squared theta multiplied by the sum of cos squared plus sine squared of psi. That will be 1. So we'll have cosine squared of theta. So to get cosine of theta, we take the square root of what we just computed. So that would be the square root of r11 squared plus r21 squared. So far, we've been looking at unconstrained inverse kinematics. This is how we refer to it in the textbook. There's another strategy of doing inverse kinematics analyses using an underlying skeletal model. And this we refer to as constrained inverse kinematics. By constrained, I mean that we require the joints to remain intact, and we disallow the body segments from changing size. In a way, we're using the skeletal model as a filter. So any part of the marker data that's due to noise or soft tissue artifact, any of these types of error, we can remove by allowing only certain motions in our skeleton. A.J. Seth used this strategy to model the shoulder. The shoulder is a very complicated joint. Specifically, he modeled the scapulothoracic joint, not a true joint technically, but he modeled the motion of the scapula as it moves over the thorax, which he's represented with an ellipsoid. And the scapula only has 4 degrees of freedom relative to the ellipsoid, which removes some noise from the measurements. So using this model, he was able to tolerate a greater amount of noise while still having clinically relevant measurements. So in the last video of this series, we're going to look at filtering. So I'll see you there.